And so my goal is to try and prove that to you. So we're still on hypothesis. In fact, all of chapter 8 is going to be hypothesis testing. And the difference here is that you'll be able to do almost all of it using SALT. So it's going to reduce a whole load of number crunching and having to go here, there, and everywhere to get what you need. There is still a fair amount of work in the questions because you have to set them up and do all sorts of things. So what's the difference between 8.1 and 8.2? The main difference is sigma is unknown. You do not know what sigma is equal to, which is actually more realistic. Can you imagine? It'd be quite rare for you to know what the population standard deviation is, mostly because you don't even know who's in the entire population, right? You get little snapshots of it, which is what a sample is. But, you know, there's a huge number of people in that population, then it's hard to tell what that is. So when you do a sigma unknown, that means we will be using not Z-scores, but T-scores. Remember the student T-distribution? The T-score. Thankfully, the calculator has SALT. Now, I don't know why it didn't do SALT in 8.1, because it could have been done, and it probably would have made your life a lot easier, but it is what it is. So you're going to get a story, but in this story, it's going to tell you all these things in whatever order it decides. You're going to have an X-bar. They're going to tell you the mean of the sample. There's going to be a guy called S, the standard deviation of the sample. Okay, you don't know the population standard deviation, but you do know this, right? If you've got a sample, you can always find this, right? You'll know how many items are in the sample, right? I did a sample 10 people or 2,000 people. And in fact, if you know that, don't you also know what's called the degrees of freedom, which is one less than that number. So if there's 10 numbers in your sample, there's 9 degrees of freedom. You'll also be told in the story what significance level, and indirectly, you'll be told HA. I know the book calls it H1, but I refuse to call it H1. HA, the alternate hypothesis. And what is that guy? That's a statement that you're trying to see, is there enough evidence to prove that it's probably true? So somebody's going to say, I think these ducks weigh more than £5 on average. I think American football players' IQ is less than 95, right? There'll be a story like that. Or I believe that the blood level, that this glucose level that this person's got is not 82. So you get a less, a more, or a not the same as. They're the 3 types of hypothesis tests. And when you get these, they always end up being HA, well, I could write them down here. The 3 versions that you get would look something like this. You believe that the answer is bigger than 50, right, the mean. You believe that it is, I don't know, less than 90. And you believe that it's not 13, right? And each one of these is a version of an hypothesis test. And what we do is we try and find out, is there enough evidence to prove this? And the way that we get that evidence is that we hope that this sample is extreme enough, right? So unusual that this has to be true. Now, for every single one of them, isn't there a null hypothesis called H? Not. But the null hypothesis is always this guy equal, this guy equal, or this guy equal. So you are after evidence to prove this. The first one equals 50. The second one, you assume that it equals 90. And the last one, you would assume that it's equal to 13. You know, that's not really different from what you did in 8.1, isn't it? It's just the number crunching was more involved. Are we good so far? So first thing I'm going to do is do a little skill building exercise. And it's how do you calculate p-values using what's called the t-statistic. So if you knew what the t is, let's suppose it's this number or that number or whatever it might be, how do you find it? Right. If the t-statistic is a negative number, then the p-value is the probability that t is less than or equal to this. If it's a positive number, it's bigger than. Isn't that just the same as you do with a z-score? Right, you get a z-score of 8, you want, what's the chances that z's bigger than 8? If you get a z-score of negative 2.1, you try and find out what the chances are that z was less than that. And another thing, all p-values depend on the degrees of freedom. That wasn't true in 8.1. So if your sample's got 100 people in it, you get a different p-value when there's only 20 people in it. And then a nasty little thing at the end. If your test is two-tailed, which is this last situation here, right, with the 13s, if it is two-tailed, SALT will tell you the value, right? You just have to remember to double it. Okay, so I have set up a kind of practice sheet where we're going to look at finding p-values. And we're just going to assume somewhere by magic, you're told this t-score and you're told this degrees of freedom, right? So we're not interested in right now where they came from. We're just saying, oh, I know what they are. So from those two things, we're going to calculate the p-value. So if I hit the SALT button, you will see, whoops, I have to do this kind of on top of it. You'll see this. Now, the guy that we want isn't the normal distribution. The guy that we want is the t-distribution. So that's the first thing that you change, right? So you make sure that when you hit SALT, that you don't just use the default normal distribution, you change it to the t-distribution. Now, the degrees of freedom in this question were 11. So if I rub this out and put 11 in, so far so good. Now, I wonder how I'm going to do this. I'll do it like that and then shrink it there. Is that going to work? No. Oops. Let's see if I can shrink it down a little. Right now, to do the picture, the numbers might be quite small, so I'm not quite sure whether. I think it's better to see the numbers and not be too worried about what the picture looks like. Okay, so t-distribution 11. The first question was a 2.92. Now, in this question, a 2.92, won't it be over here going to the right? So I would say right-tailed, and then here I put 2.92. And you see this little guy here? That's your p-value. So in this case, it's 0.00697. There you go. Right, do you see how I got that guy? So Next one is going to be 1.89 and a 34. All right, so here we go. 34 degrees of freedom. 1.89 is to the right. Positive, you get a right tail. 1.89. And then when we click off, there's our answer. Are we good with how I'm doing this? I mean, I have to move a fair number of windows around, but hopefully it's not too bad. Right, the third one, negative 2.59 and 7 degrees of freedom. 7 degrees of freedom. Negative 2.89. Now, when it's negative, don't you want, oops, negative 2.89. There we go. Do you see that I had to choose a left tail first and then put in the number? And here is the p-value. Making sense? So you're going to have a fair number of questions where you're going to have to figure out what the p-value is from the data. So let me move. This guy out the way and show you a added problem. So here's the first question. The first one where we use salt. 11 degrees of freedom and a 2.92, right? No biggie there. So when I hit salt, I have 11 degrees of freedom, 2.92. Oh, I've just done that one. Right, it's that guy, right? But you don't actually type in, which is how I would have done it if I was writing this, the number. For some reason, better known to the people who wrote this textbook, do you see that there's a whole load of dots? And the one that we choose is the one where our number is in that region. Now, the one I want to do is, let's say, is a two-tailed test, right? Now, for a two-tailed test, what do you do with this number? This p-value. When it's a two-tailed test, you double it, right? Now, if you double that number, can you trust me that the answer that you get is in the range from 0.01 to 0.02? So every time you get one of these p-values, you don't write down the number, you pick the interval that your number is in. So I guess if you were only doing it to like 3 decimal places, it wouldn't matter because you'll still be in the same interval. So maybe that's why they did it. These answers are bugging the heck out of me. Okay, that's good. So I'm going to return now for a little while and show you a kind of standard question. So here's a made-up one. A zoologist believes that the average weight of a new species of bat is over 5 pounds. Right. So they've just discovered in this cave a new species of bat that nobody else has discovered. And they want to get kind of statistics on it, right? This new bat on average weighs more than 5 pounds. On average, you know, its wingspan is this. On average, its number of babies it has in one go is whatever, right? They collect everything you could possibly think of. So in this case, it's the weight. And he thinks, or he believes, that it's over 5 pounds. That's fair enough. He's going to test this hypothesis. So this is like what the question looked like. And he collects a sample of 12 bats, and that the average weight of these bats is 5.6 pounds, and that the standard deviation of the sample was 0.6 pounds. Is there enough evidence to show that the average weight of these bats is over 5 pounds using a significance level of 5%? You know, all hypothesis tests are with a significance level, right? It's 5, 1, 5, or 10, right? That kind of thing. So I got this story, and we're going to look at my little collection list, right? And we're going to see, have we got everything that we need? Actually, I want this here. I'll just squeeze that over there. So you won't be able to see it, but I can see it. So in this, we need all this. So that guy there was 5.6 pounds. The standard deviation was 0.6 pounds. The number was how many people in this sample, and that was 12, but doesn't that mean that the degrees of freedom are 11? The significance level here is 0.05, and that was in the story. So if you like, that's pretty much almost everything that was in this written format has now just been condensed into its essence. Now, you very often get questions that ask you, that fella, right? A null and the alternate hypothesis. In these stories, it's all about the mean, right? It's all about mu. Is there enough evidence to show that the average weight of these bats is over 5 pounds? Are you happy about how I wrote that down there? You see where it comes from? Right. So what is the null hypothesis going to say?
Equal to 5.
Equal to 5. Now, if this was 8-1, wouldn't it be a whole load of getting Z-scores, using calculator, get a p-value, using the calculator, and a whole load of fiddly stuff with sigma over root n, and a whole load of stuff that took forever and a day, and it's so easy to put the square root in the wrong place or forget a decimal, or you just get frustrated as heck. Well, not anymore. We can do everything that we need, which is basically, we're just going to get the p-value. Get right, do that whole chunk of work. But salt is going to do it for us. So let me show you how we do that piece of the work using salt. I just hit the wrong button. Darn it, in space. I am so pleased that I don't swear. That shows you self-control. Right, Holly? Oh, wait a minute. You were in the military. Forget self-control. You'd be swearing by now, wouldn't you? Yeah. Okay. So I'm just going to pick that box, because once you get into salt from any question, right, you just hit a salt button and it gets you in. Right, when I hit this one, the world's going to change a little bit more. I am not going to use this one. That's the one I used for those warm-up questions. The major set of questions is going to happen here. Now, do you notice it's called inferential statistics? I might make this a little bit bigger because I'm not quite sure how good your models are. Right, can you see it? Inferential statistics. Now, one sample T. Now, if I click on that, there's lots of other choices, but one sample T is exactly what I want. Now, in various boxes, all the stuff that I have in this piece of paper, right, which you can maybe see, right, is going to appear. Right, the sample mean was 5.6 pounds in my story. The sample standard deviation was 0.6 in my story. The sample size, not the degrees of freedom, but the sample size was 12. So you don't even need to take one away, right? It'll do that for you as well. Isn't that nice of them? Now, the hypothesis mean is their way of telling me mu equals 5. Right? Now, I wanted mu to be bigger than 5, right? That's written down in paper. Mu greater than. Now, my English or my brain is saying that's annoying. Shouldn't the greater than be first and the 5 should be second? It just looks funny, right? But that's the way it's set up, so I'm going to live with it, right? Are you okay with the fact that the statement is after the number when it really makes more sense to switch places? Right, now everything there that we want is set up. So there's a big green button, generate result. Would you look at the null and alternate hypothesis? Right? And lots of stuff, but the only fella that really matters was the p-value. Do you see the guy right at the end? Because all those other numbers, weren't they just what you would need to calculate if you were going to do it by hand? But the bottom line is we now have a p-value. In this case, it's 0.002647. So as long as you have that little hit list, right, with all the good numbers in it, can't you go over here and let it do the rest for you and get your p-value? Now, I know I have to jump back and forward a lot, but now what can you do? I'm now going to kind of show you where we go from here. Right, there's that p-value I just got, right? Now, what's going to look funny in your homework is that you won't get that. You know, you get one of these little dot things, and it'll say your p-value. I don't know. I guess I should start it from 0 to 0.01 and 0.01 to 0.02, 0.02 to 0.1, 0.1 to 0.2, right? Lots of choices like that, right? They don't even need to be equally spaced. Don't you just look at your guy and say which dot he belongs to? So in this case, lots of zeros. I would put that one there, right? In that particular question. Suppose that was a not equals to 5. Could happen. Then wouldn't you do something about this fella? You double them, right? So.
Professor?
Yes.
So when you said it's equals, there is a question in the homework where it says, suppose it equals this. So could you pick either more than or less than and double it? Or what would you do with that?
Oh, you mean if this says not equal to?
So I'm saying, so there's a problem. It's in the same format with the inferential or whatever on the salt.
Yeah.
But it says conduct a two-tailed test to claim that it is something. So that's not a not equal to, that's saying it is something.
Okay, so let's look at this fella here and see if I can duplicate what you're talking about. Right, can we pretend that the guy didn't want to prove it was equal to 5, he just wanted to prove that it wasn't equal to 5, right? Now, when I hit generate results, do you see it's already doubled the p-value for me? I mean, if you double the 0.0026, you see it's now doubled up to 0.0052.
Okay.
Right. So I hope that's what you're getting at. Okay. So let's return back to, oops, I got a chat. What we got in the questions? Yeah. And the significance level, as someone mentioned, would be in the story. Right, so for my story, the one about these ducks, or bats, I think they're bats, we got our p-value. We won't type that in the homework, but we'll choose an interval that that number is in, and that'll be how you do that. And then you get the, is our p-value less than our significance level? Because if it is, won't we then be able to say statistically significant result, these bats are heavier than 5 pounds, right? That thing. Is this p-value 0.002647? Is it less than 0.05? And if you do a quick scan, the answer is definitely yes, isn't it? In this question. Isn't that decimal smaller than the significance level alpha? Now, you don't typically write that down, but I physically write it down. And think about in an exam, even although you're using salt, with the exception of that bit, wouldn't you, I would suggest strongly that you write all this down. That way I can see that you were using the data and what you were using and what you thought the thing was and what the test was. Now, when it is yes like that, doesn't that mean then that we have, I'm phrasing it different ways, but it's the same meaning, there is enough evidence to show that, what are these bats? So we could say a phrase like, it's statistically significant result here that these bats do on average weigh more than 5 pounds. In the jargon, there's enough evidence to reject H naught, and therefore the alternate is true. So that's kind of the lawyer way of saying the same thing. Are we okay with this first dummy run of how we're pretty much going to use salt to do a fair amount of the heavier lifting for us? So what we need to do now, I think, is, okay, where are you hiding? I can never find things when I want them. Oh, I know what we're doing. Here we go.
My neighbor's having an emergency. I'm gonna have to go figure out what's going on. I will see what's going on and try to log back into class, but I'm gonna go.
Okay, Denise, not a problem.
Thank you.
Oh, come on, go away. Don't want the solutions to the key, it's annoying. Right, what I'm going to do in a few seconds once I've got all this stuff out the way is, we're just going to go through some questions and get used to the way the calculator, get used to the way that WebAssign does it. Right, the first couple of questions are all to do with just what does a significance level mean and what's H naught and what is A and all that. And this question here we've covered, right? Find the p-value, and then it's one of these. Find the p-value, it's one of these. And here is our first question. So question 7. So a random sample of 16 values is drawn from a mound-shaped symmetric distribution. Well, the reason they're telling you that is that the reason we can get away with what we've been doing is that we've made the assumption that the distribution is not weird and, you know, skewed and all sorts of stuff. it's basically a hill. Maybe not a perfect hill, but good enough. Now, a random sample of 16 values is drawn from a mound-shaped symmetric distribution. The mean is 10, the standard deviation is 2. Use a significance level of 0.5 to conduct a two-tailed test of the claim that the population mean is 9.5. Right, so they didn't even bother giving you ducks or bats. They just said, here's a story without even the context to it. So I'm going to take what's there and write it down in my little hit list. I'll try and be consistent, so I'll find the other one. So the kind of things I need to know to be able to do this question. Don't I need to know the sample mean X bar? And that's 10. I also need to know how many people or things, in this case 16. I also need to know the standard deviation, which is 2. And the last thing I need to know is significance level, and that's the data. And then I have a null alternate hypothesis, and that's coming out of the end piece. A two-tailed test of the claim that the population mean is 9.5. What on earth is that doing there? It's just the way they phrased it is freaking me out. I think it's the other way they put the numbers in the tables. So let me show you what the heck they're asking, and I wish they'd asked it in a better way. Oh, there's all the information. 9.5, not 9.5. I'm not quite sure why they want to phrase it in that weird way, but I guess you have to live with whatever they phrase it. A two-tailed test of the claim that the population mean is 9.5. To me, that has to be this way. Why? This has to be equal to 9.5. Right? It just has to be, right? And so what would the alternate, the opposite of that be? Well, not 9.5. Right? I would have phrased that from the other perspective. Is there enough evidence to prove that it's not 9.5? Maybe it's just the English language. Right. So now that I've got these numbers, I'll go back as we bounce along here. And is it appropriate to use the student t distribution? That's what we call, you know, the t guy. Like Z is called the normal distribution, t is called the student t distribution. And yes, because it's mound-shaped. How many degrees of freedom? Right, this guy had 16 data points, so 15 degrees of freedom. Can we pick that one as the null alternate hypothesis? Now, compute the t value and then do your test. Okay, right. I haven't calculated t yet, but I will come to that in a minute. We are doing a significance level of 0.05, agreed? So our p value has to be less than 0.05. So which one of those is less than, is a p value? Okay. Let's come to that in a minute. All right. Going to compute a t statistic. So I'm using this guy again. The mean is 9.5. The mean, sorry, is 10, mean of the sample. The standard deviation was 2. The sample size, not the degrees of freedom, was 16. This fella was 9.5. And we're doing a not equals, so I should be able to generate the results. Oh, the t statistic is 1. So the t statistic is 1. The p-value that I got was 0.00529. 0.00529. And the p-value 0. God, that's hard to do in your head. 20529. Oh, it has to be that one, right? I'll just try to find out which interval had 0.0059 in it. Right, do we reject this fella? Right, is that p-value small enough to reject H naught? Is 0.005 less than 0.05? So the answer is yes. And when it's a yes, you reject the null hypothesis then. And then there is insufficient evidence. A little bit confused by the phraseology of that, but I can live with it now. Okay, here is a big long story. So hopefully they won't do anything weird in the way they phrase it. And we're going to go through the same process. I'm going to collect all the information. Then I'm going to use SALT to find the p-value and maybe the t-value if they ask for it. And then I'll come up with my conclusions. So WeatherWise is a magazine published by the American Meteorological Society. One issue gives a rating system used to classify northeaster storms that frequently hit New England and can cause damage. And so a severe storm has a wave height of 16.4 feet. And it goes into real details. The information I need is, what sample did you take? Let's see. 37 waves, so n is 37. So that piece there told me what n is. If I read on a little bit further, can we see that the average is 17.3? So there's my X bar. They're calling it sigma, which is a little bit. Oh, I know why. I shouldn't have done 8. I'll make sure I take it out, but before I take question 8 out, what's 8 got that it shouldn't have? It's got a sigma, doesn't it?
It has
And
sigma and mu.
Right, so wouldn't that be an 8.1 question? In which case, as you can see, there is no SALT. And I think we've done enough 8.1 questions that I can kill that one. So just pretend I never asked you.
Oh, that's
I
why I
should
got
have-
that one wrong.
Oh,
I
okay.
was using the wrong process. I was like, what is wrong with this?
Yeah, well, I should have been careful. That's my fault. I should have realized when I didn't see the SALT button that there was something strange about that question. Right, so pretend I never even did that one. This one's boring. Okay, that's boring, but we'll do it. Question 10. A random sample of 46 adult coyotes. Okay, so you just told me that N is 46. The average age of them is 2.03 years. Well, that tells me, forget about the story for a minute, coyotes don't live long, at least not in the wild. I mean, if the average age is 2, can you imagine there's little cubs, right? They're like 0 virtually. And then the old ones in the family are probably about 4 years. So, yeah, I don't know what, a coyote probably doesn't last that long. I guess maybe that isn't a surprise. Okay, standard deviation, 0.76. I need a significance level, which is right at the end. So what's the significance level? That was a pretty simple question, 0.01. Right. Oh, and we need a story. Here it is here. Does the sample data indicate that coyotes in the region of North Minnesota tend to live on average, to live longer on average than 1.75? So we're being asked this guy. Right, you see all the information that we've got from that story is now here. What's missing up here? What's missing here?
Mil equals 1.75.
Right, are we getting so comfortable with that I can stop asking you that question now? Okay, good. So I'm just going to write it from now on. I may ask you what this one is, because you may have to think about that, but not this one. Okay, so although you can't see it, I'm scanning through the choices for the one that did exactly what you just said, and you'll trust me, it's the third dot, right? So there's a whole load of dots, and one of them, the third dot, and that's how you write it down. So, you know, that's just how the homework gets it, right? You have this, but you pick it from a list. And then it talks about what sampling distribution to use. And we're going to use a student. And then the rest of this is going to come from salt, which means I'm going to have to leave this and go into salt and use all that information that we have. And here goes. Ah! Okay, this fella was 2.03. The guy next door was 0.76. And this was done on 46. The hypothesis mean is 1.75. And we want to know, is it greater than? That still bugs me. I mean, how hard would it be to switch those two things around? I mean, how hard would that be? Anyway, we got what we need. Do you see all the numbers, where they go? And how you kind of have to do a little bit of cryptic on the null hypothesis, alternate hypothesis. Right, generate results. That looks good. The fella that we need is a T statistic, which is 2.498753. And then the p-value, which is 0.008091. Okay. So if I go back here, what is the test statistic? That's what they are calling the t-value. Can I just do the 2.49 and you can imagine the other 8 digits, right? Now, estimate the p-value. Well, we didn't estimate it, we got it. It was 0.008. So 0.008 means it's that dot, isn't it? It's in that range. Now, do a little sketch of what does that look like. Well, it looks like a really tiny guy. I'm guessing it's that really tiny guy. No, I'm not. Why should I change it to that really tiny guy? Because it could have been, in some questions, it could have been this one. But in this question, it's that one. I am looking for bigger than, so it's a right tail test. If the story was less than something, it would be a left tail test. Right. So that's where that came from. Now, we already know all the good stuff. At the 0.01 level, our p-value is tiny. So we would say yes. Which is that? And which is that? Are we good on that? God, these take longer than I was hoping. That one's a bit trout. I don't know if I want trout. No, I don't want stocks. Ooh, okay. I'm sure you all want to know about arsenic in our water. That should cheer you up. Unfortunately, arsenic, I think isn't arsenic CN, carbon and nitrogen bonded together?
Isn't that cyanide or is that?
Oh, it could be cyanide. Yeah, I think arsenic isn't arsenic just a metal? It's pure. It's in the metal.
Arsenic is just AS. It's just like its own element.
Yeah, so I think it's in the metal family. I don't think
Yes.
it's right. Okay, no, that matters. One darn thing. It's just my brain wandering. Unfortunately, anyway, lumps of metal called arsenic occur naturally in some groundwater. It's a bit like getting rust in your water, right? You could get arsenic in your water. A mean arsenic level of 8.0 parts per billion. Okay, can you imagine 8 atoms of the darn thing in a billion atoms? So I don't think we need to worry about your water, right? It's considered safe for agricultural use, okay? A well in Texas is used to water cotton. This well is tested on a regular basis for the arsenic level. And here's the numbers coming up. N is 41, so I'm writing that down. X bar is 7.1. S is 2.2. And the significance level is 0.01. And does this information indicate that the mean level of arsenic in this well is less than 8? So less than 8. Hold that thought, less than 8. There's all your usual data. That's going to be 8, right? I promise not to ask you that again. What's this one going to be?
Less than 8.
If you read, as long as they phrase the question in a very mathematical way, it's dead easy. Sometimes you've got to be careful with the English language. It's no more than 8. Is there enough evidence to show that it's no more than 8? It's the same thing, but you know, the English language can sometimes have double negatives in them or whatever and really throw you. Right, that should be ready for assault then. I'm not going to answer all these questions. I just want to get practice at typing in the good stuff. So in this case, it's going to be a 7.1. The standard deviation of arsenic is 2.2. The sample size was 41. So there's 41 readings. And is it 8 or is it less than 8? Okay, set all the data up now, getting kind of, you know, more you see, the easier it is to figure out where they all the little bits go. Generate the results. If they want that number, type it in. Oh, this is getting a little bit boring. Isn't that p-value really tiny?
We can't,
Oh.
or at least I can't see the.
Well, I'm typing in great here and nobody can see a darn thing. There. There's all the data. There's the p-value. Tiny. Is that guy going to be less than 0.01? Yeah. Is it not going to be statistically significant? Therefore, you can say for sure that there is less than 8 in this well, in which case the guy is probably going to be able to keep using the well to water his cotton crop. I wonder if it gets too high, what they might do is that well's polluted with arsenic. You can't use it for crops or drinking or probably anything. Seal it up and, you know, nothing to see here. Right, move on. We're getting better. Every time we do one, it gets a little bit easier. What I'm hoping I'm generating here is there a process that you can see I'm going through? I'm getting the X bar, the S, the N, and the alpha, and the null alternate hypothesis. Then I'm going into SALT, putting in all those numbers and finding the p-value. And once I know the p-value, I can tell if it's statistically significant or not. Every single question I've picked, either by luck or design or whatever, has been statistically significant. Every single one of these p-values has been very small. So I'm going to not do one of their questions. I'm going to make up one so that we can see what the heck it looks like when it's not statistically significant, right? So let's suppose we wanted to collect data on the average age of students in this class, and I'm going to pretend that we're not collecting it. And we collected it and we found out that the average age was 24 and that the standard deviation was 5 and that there was 30 students in the class and the significance level that I'm going to choose was that one. And we want to know, is there enough evidence to show that the average age of OC students is less than 25. Well, my sample is a clear indication that that may be true, but it's not statistically significant yet until we've done the process. So I'm going to use these numbers, and I forgot my little guy. And less than 25, right? So I'm now returning back to SALT. And I hope I've picked these numbers so that I get a reasonably big p-value. You're not ever going to get a p-value 22. In fact, because p is a probability, isn't 1 the biggest it's ever going to be, right? So you know it's going to be 0 point something. But I hope at least it's, you know, relatively big. So that's what I'm going for. So here we go. I got the salt. Are you looking at the salt, guy? Right. So I'm going to change this one to the sample, which was 24. I'm going to change the standard deviation to 5. I'm going to do a sample size, which was allegedly 30 students. This fella is 25. And is there enough to prove it's less than, right? So pretty much the setup, generate the results. There's our null alternate done for us. There's a t statistic. Yay, good. I'll write this fella down. We got a p-value of 0.14 and some stuff. Right, when you look at this fella, when I do the test, is the p-value less than the significance level alpha? We are looking at, is this decimal less than 0.01? Do you see the answer is no, it's not. So that would be not statistically significant. That there is no evidence to, that isn't strong enough evidence anyway, to prove anything about the age being less than 25. So big p-value just means bigger than alpha, right? I mean, that's a pretty small number, right? But it's bigger than alpha. That's all it needs to be. If I decided that I didn't like that alpha, if I had decided that I was going to just use that one, would the answer still be no? Is my p-value less than this though? No, agreed. So no matter what significance level I chose, and there are only 3 really to pick from, would you agree that nothing statistically significant came out of that sample? Now, if you were interested in getting the answer to this question, the only thing that's left is do it again, but with a bigger sample size. Can you imagine an unscrupulous guy finding out what the p-value is? So we calculated the p-value, and it ended up being 0.08173, right? So imagine that was my p-value. Once he saw that, then he would choose the alpha. Can you see that's cheating? That you're picking the alpha after you've done the experiment. Alpha must, if it's an honest experiment, an honest statistical process, is always chosen before you do any analysis. So if you were looking at a set of reports or data, and they were telling you that here's 12 areas, and in this area it was statistically significant, in this next one it was there, let's suppose they're counting arsenic levels, right? And they had 12 different wells, and every single one of them, it ended up being statistically significant that there was too much arsenic in the well. And you might think, oh, that's not good. If you look into it and you find out that in the first well he used a significance level of 0.05, The next one he used 0.1, and the third one he used 0.01. Anybody who knows statistics knows exactly what that guy's done. Didn't he keep cherry picking his alpha for each one so that he could say it was statistically significant? For instance, statistical significance of that, doesn't that mean 10% of the time you're wrong? Right, the hypothesis test says, yep, you've proved what you wanted to prove. Well, yeah, but 10% of the time when I say that, I'm wrong. And so you don't want people doing that. So how do you get around it? In good scientific data, medical data, science data, whatever it is, you always find the p-value. So if you look at the bottom, look where the little asterisk lives, right at the bottom of the page, you'll see a little thing, looks something like this. P equals 0.073 or something. And then that's where I look and I say, oh, okay, what you've just said is probably right most of the time, but isn't there a 7% chance that you're wrong? So don't treat statistically significant as meaning that guy did the murder, right? Or A definitely caused B. Think of it more as that's where the evidence is pointing, but it might not be true. Are we good? Time for one last one? Right, who are we going to pick? Let's do student participation. I'm going to show you what questions are left, and you're going to pick one that you think's more interesting than the others. And that's the one that we'll choose to do. So here we go. Are you looking at the thing yet? No. Have I still switched over? I have, haven't I? There we go. Right, there's the arsenic one that we've just done. This number 14 is about red blood cells. Number 15 is about hemoglobin count. Number 16 is about avalanches.
Ooh.
Any of those three interesting enough to want to continue? We're going to have to pick one, so. None yet? Oh,
Blood
might
count.
have. Blood count. Let's go back. I think that was. Right, this one, 14. Okay. Now, hopefully you can see that screen. So I'm going to give you 1 minute to write down the 4 key numbers that you need to use salt. So read that story and suck out of it the 4 key numbers that you need to do salt. And one of them is going to have a question mark beside it, and that's okay, because I'll show you how to fill it in. Okay, here goes. What's X bar? Don't know.
4.80.
Is it? I know 4.80 is there, but 4.80 is the one that we're going to be testing against.
It says the mean is, yeah, right?
Oh, let me check. For the probability, suppose that the mean of x, oh. Yeah, but this is for healthy people. It's 4.8. So they've told us that mu is 4.8. So how am I going to get the sample and mean and the sample standard deviation? Do you see how there's two boxes here and here? Right. Going to click use salt. Now, do you see that what we've got is this fella here? If you then click over to descriptive statistics, can you see that the mean is 4.4 and the standard deviation is 0.2828? So let's get back into the question. Use your calculator. Well, I'm using SALT to do it. So 4.8 is what healthy people have. This is a patient who's going to have 6 blood tests taken, and they're going to look at them to see if that patient is healthy or not, right? So the mean of that patient, well, darn it, where's my numbers? I'm going to have to find them again. Right, the mean is 4.4. The standard deviation is 0.282. Okay, got it now. So the mean of those 6 numbers is 4.4. The standard deviation of those is 0.2828. Does this data indicate that the blood count is lower than 4.8? That's the hypothesis test now. Hypothesis test. Is it less than 4.8? Now, the number in this sample was 6, and the significance level, although you cannot see it anymore, is 0.05. So in this question, you were told those. And these two, you had to calculate using SALT. Okay, now I'm ready to go back and find a p-value and come up with a conclusion. Just looking at the raw data, do you think that 4.4 is lower than 4.8, statistically significant lower? Or do you think that could just be random? You could get that anyway. Any gut feeling? Do you think I'm going to get a statistically significant result again? Or maybe not this time? I honestly don't know. It's hard to tell. Let's say no. Forget that guy for a while. Which one of these choices along the top is the one that I need to use?
That one.
Right. And let's put in the information. Oh, that is cool. Isn't it already typed in for us? Almost all typed in for us. Do you see they've got the 4.4 and the 2828 thing? And the sample size. So all I need to do is put in the test number. is it less than 4.8? So when I hit generate results, we are going to see a lot of things, but the one that I'm interested in is the p-value. And I want to know, is it lower than 0.05? Oh God, look how low it is. So this particular person has definitely got a blood count lower than 4.8. So it's lower than normal. So for some reason, what's blood count? Is that how much red cells you've got in your blood? Anybody? I
Yes.
don't know. Oh, that was a half guess. So your blood's made up of red blood cells, white blood cells?
White blood
Yeah.
cells and platelets.
Right. And what's the liquid that your blood flows in? Because if I've seen pictures of blood cells, aren't they little, like, they look like mints, right? They're kind of dimpled.
Disc shape, yeah.
Disc shaped, right? But they're floating in a liquid, aren't they? And that's how they move around your body.
Hmm.
No? Am I just
Wait, sorry.
wrong?
The plasma.
That's plasma. So if someone is really badly injured, can't you give them plasma as a safe thing? Because if you try and give somebody a blood transfusion before you've tested what blood they've got, can't you do them more harm than good?
Yes.
Yes, I think
Right.
that's
So
That is
if
true.
somebody got a car injury and lost a lot of fluid, blood, you could stabilize them with plasma and that would be safe. So the ambulance driver might stick an IV in you and give you some plasma, right? Just to get your blood enough liquid and hopefully, keep you moving until they get into the hospital and do the real stuff. Now I'm making that up, but that's what my brain is telling me. Does that sound about right?
I have no idea, but it sounds like it
Kind
makes
of
sense.
IV fluids. Yes. You have,
IV fluid.
you have the right concept. Yes.
Right, maybe not the right name to put to it. Okay, that's cool. So, just because I'm curious, and now we're talking about blood, there's different letters to blood, right? Like there's an A and a B and a positive and a negative and so on. But I do know, but I've forgotten what it is. So this is a test for the medical people. What blood can you give to everybody?
L.
O positive.
O positive is good for everybody, right?
Yeah.
What's the worst blood to have? If there is such a
AB
thing.
O
negative.
negative.
O negative.
Don't have O negative,
Yeah. You can
because the
only
only
get.
thing you can use is O negative.
Yeah.
And it's rare.
Well,
Maybe not rare, but don't Oh. So if you're O positive, you're can an O positive person get a B positive blood?
No, O can
No.
only get O. They can give to anyone.
But
Right.
they can only receive from an O
Oh.
plus.
correct.
So what blood group do you want to be? You want to be a B then, because you can
A-
get
You want to
everything.
be
positive
AB positive can
Can
receive
get
anything.
anything.
So AB positive people are good to go. Doesn't matter what it is, you give it to them, they're fine.
Yeah.
And O's are generous. You can give it to other
They're like
people.
the best
but-
donors. Yeah.
Yeah.
So if you're an O, you're really good. The blood banks, they like you, don't they?
Mm-hmm.
So do they keep the O for special occasions and use up the other stuff? Because, if you suddenly need a lot of blood and you don't want to have to test people, you can give them that blood and you know it's going to be safe.
Right.
Right. So that kind of makes sense. And it's genetic. Don't you get your blood groups from your parents?
Yes.
Is there any particular combination that generates O? Both parents have to be O, or just one?
O is a recessive, so both have to be O. I mean, well, actually,
But
they both have to carry the O gene. It
yeah.
doesn't mean that they are O.
But if you have O blood, both of you, then you have O kids. But you could become O if like both of your parents have A,
Yeah, they
But
have
I
like,
can
because
go in them.
like he said.
A or B is going to be dominant and it's going to cover up the O. For example, if they have
Right.
like their alleles are AO or BO, then they'll be A or B. But if both
Right.
parents are AO, then there's a chance that their kid could have OO, which would make them an O.
Right. So if you've got an AO and a BO, 1 in 4 kids will be an OO.
Yeah.
Yes.
Right. And the other 3 will be an A or a B. See the cool things that we learn in this class? Right. Okay, I think we've did enough today. I hope that you're getting the idea of how SALT works. I have to kill question 8. If there's another one in there, I guess I should check. But if I miss one and you turn around and say, yeah, do you know question 13 is a Z-score guy, it shouldn't be there, tell me it and I'll make sure I take that out. But as far as I know, 8 was the awkward one.
Can we
Josh,
just
did you
do it
find another one?
For practice?
Say again,
No, I
Jennifer?
didn't. But
Can we just
8
do it for practice?
What, the Z one?
Yeah.
Sure, we can do that. If you're interested, just hang around and we'll do question 8. I'm going to have to close off a whole load of windows just to get back to it, but that's not a big deal. And what that means is that we're not going to use SALT at all. We're going to use good old-fashioned calculator and just number crunching. Right. So first I'll find question 8 so I can use the right numbers. Right. So stop share, go in, here we go. So the reason I know this is 8-1 is sigma is known, right? If sigma is unknown, it's going to be a T distribution, it's going to have a SALT button, right? But in this story, sigma is known. So a lot of the information is exactly the same information, right? With one major difference, the sigma guy. So this particular one was about northeasters. I've already got X bar, so I'm just writing that down, 16.5 feet. I know sigma in this case, and that's 3.5. And somewhere in this story, there's an N. Can anybody see an N anywhere yet? It may be that it needs to be later on. Where are you, N?
$37 waves.
There you go. It was, I knew that, I missed it. Now there's a null and an alternate, just like we've been doing, and it's the same kind of story. It's a mu equals and a mu bigger than, less, or different. And does this information that the storm is perhaps temporary increasing? So is it greater than? And increasing in this world means bigger than 16.4. Right. See that guy there? Is it bigger than that guy? So I think I've collected all the numbers that we need. So we're now going to go into what we need to do to get our answer. 16.5, yeah, it is bigger than 16.4. Significance level 1%, sample size 37, sigma is a given value 3.5. So step 1 would be create this. Essentially step 2 is collect your data. Step 3 now is we're going to get a Z-score. And the formula is X bar, take away mu over sigma square root of n. And that's going to be 16.5 take away 16.4 divided by 3.5 square root of 37. And I'm putting brackets around everything in sight because I'm pretty sure that that's not going to be a very nice looking answer. So let's see what we get here. A bracket, 16.5 subtract 16.4 divided by, I put another bracket in, 3.5 divided by the square root of 37. And the answer I get is a very unremarkable 0.174. I already know this is not going to be statistically significant. How can I tell just looking at that Z-score that we're probably not going to get anything decent out of this? What kind of Z-scores give you interesting
low.
results, if I phrase it that way?
Ones that are higher?
Yeah, and typically anything bigger than 3 or less than -3 is like a slam dunk, right? You're going to get statistically significant results. You can still get them out of 2 point somethings as well, but that's a bit harder, but it can happen, right? Right, so that's the Z-score. To calculate the p-value, we find the probability that a Z value is greater than this Z-score. And that becomes this calculator thing. It's called normal CDF. And you want 0.174 or bigger, comma 0, comma 1. And the 0 and 1 are there because the mean of a Z-score distribution is 0 and its standard deviation is 1. The 9 is there because it's bigger than that number, but couldn't I put 99 or 20,000, whatever I felt like, and it would still work? Now to get this fella, again, it's a calculator job. Second distribution, choice number 2, hit enter, and then you would type in 0.174, comma 9, comma 0, comma 1, and nobody is going to be very successful with a p-value of 0.431. Well, I should check it. Shouldn't I check it against 0.01? Well, is my p-value less than alpha? Is 0.431 less than 0.01? An emphatic no. So it's not statistically significant, and therefore you don't reject the null hypothesis. Are we cool with that?
Yep, thank you.
You are welcome.
See you Wednesday.
Yeah, that's right. See you Wednesday, everybody. Oh, somebody remind me next week to get people to double vote because I forgot to say hi today, and most of you have left.
Yeah, everybody did.
Yeah, so you will tell me tomorrow, Wednesday, Jennifer, double vote. So
Double
you'll say hi twice if you were here twice, right?
Okay.
So you'll say hi, and that means you were here Monday, right? Okay.
Sounds good. Bye.
Bye-bye.